So, we are live. Welcome to this workshop of solving differential equation in parallel on GPUs for the JuliaCon 2021. My name is Ludovic Ress from ETH Zurich.
Hey everyone, I'm Mauro Werder. I'm also from ETH Zurich and also VSL from near Zurich. And I'll be, I guess, co-hosting this show.
Hello, I'm Samuel Lomlin, a computational scientist and responsible for Julia computing at the Swiss National Supercomputing, which is also part of ETH Zurich. I will be just assisting in the question and answer.
Okay. Well, then here we go. Before we dive in, a couple of general information regarding the workshop. So the workshop material, as in the session description, is available on Git at the address you see now in the banner. So if you go to that address, you end up on this extended README, where you will find all the important links and all the materials. So like all what we present today and we'll discuss is written down in the README with links to different sections, link to the codes, and also like some information regarding the startup for people who are not yet set and ready to go. So like we just made some quick updates before start, so please fetch the latest version. And yeah, if you are further interested or you want to check out further material, there are two links here. So there is a online GeoHPC tutorial that covers overlapping topics as we'll discuss today. And there is a similar README and a kind of workshop assembly that we gave at EGU, European Geoscience Union's General Assembly this spring, that covers maybe more the ice flow application side that we use as overall driver for why to do all this development here. So yeah, with this forward, I'm set, and I think I'll pass the mic to Mauro, which will kickstart that event. Oh yeah, maybe, sorry, one last point. So the Q&A will occur on, Q&A will occur on Pigeonhole, like for those who knew it from other workshops. And yeah, we'll try to take some time to answer the questions live. And there will be some, I think over the 3 hours, we'll try to make some breaks, at least two breaks and the final Q&A. And during the breaks, we'll try to answer some live questions if there is need for it. But Mauro may say some more words on that. Mauro, it's over to you.
Okay, well, thank you, Ludovic, and thank you, Ludovic, for putting this course together. This is really 99% Ludovic's doing. So thanks a lot for this. I think it's great work you did here. So what are the objectives? So the goal of this workshop is to offer a view on how to solve systems of partial differential equations in parallel on GPUs. And we'll be using these parallel stencil and implicit global grid Julia packages. And so parallel stencils allow us to do architecture agnostic stencil computations. So we'll be doing finite difference computations, but you could also do other stencil type computations. And it runs both on the CPU and the GPU. So you can program at the same time for both. And then in the last part of the workshop, we'll be using implicit global grid, which then helps to parallelize your code on one GPU or one CPU but many. So think about a kind of HPC context where you want to use MPI to distribute your work. We'll be using well, as an example, we'll be using a nonlinear diffusion equation. So I guess one application there would be to solve ice flow, which is what we do in our day job. We're glaciologists, or at least Ludovic and myself. Yeah. So here's an example from Greenland model run. Yeah, so there's 3 parts to this workshop. I'll be talking about part 1, and Ludovic will be doing part 2 and part 3. I'll get into the what this is about in a moment. And I think the important bit about this this repository is really the scripts folder, where all the scripts we talk about are located. There's also an extra folder where extra scripts, which we're not going to cover today, are located, but for those of you who are interested. Yeah, so to getting started, so some of you may have already visited this repo. If not, the fast way, if you have Julia installed and whatever, yeah, and you're set up, you can just use these commands here. So you clone the repo, you cd into the scripts folder, you start Julia with the project and with 4 threads. And you can do using pkg instantiate, and it will install all the needed packages. So it'll take a bit of time, but yeah, you'll get there. And then you're set to run the scripts, which we use now over the next 3 hours. So the workshop material, so as I said, is grouped in 3 parts. So the part 1 is I guess it's really iterative solvers. So that kind of lays the basics on the equation we solve and a few basics on the methods we use. Then the part 2 is then how to move this parallel computing. So on the CPU, and then the GPU. And so the plan is to cover these parts here in the first approximately hour. Then we take a break. Then yeah, and have some questions and answers and actual break. Then these 3 are probably covered in the second hour, and then another break, and then this part here in the third hour. So here the second hour is then really the GPU implementation. So that uses then a parallel stencil. Yeah. And then the third part is then how to distribute it to multiple nodes. So that's then implicit global grid. And maybe as a shout out to Sam. So he's really the mastermind behind those 2 packages, parallel stencil and implicit global grid. Yeah, so those were really his babies. All right, so without further ado, let's actually get down to business. So fast iterative solvers. So we'll first try and find a way to implement efficient implicit iterative and in particular matrix-free solver to solve time-dependent nonlinear diffusion equation in 2D here. But the method we are actually using is general, so you should be, in principle, be able to solve any nonlinear PDE with this method. So let's start. The diffusion equation here, it's stated. So we have a quantity h which diffuses. So the time evolution of this quantity, dh by dt, is equal to the divergence here of the flux of the quantity. And we want to make a nonlinear, so we have a nonlinear flux. So this is the gradient of this quantity, and we times it to the quantity to the power of 3. This is actually pretty similar to the ice flow example you saw above there, where in the simplest kind of case you have this kind of nonlinear diffusion equation. But it pops up in many other places as well. So we can describe this equation here, break it down into a flux in x direction. So this is this h to the power of 3 times the gradient of h in x direction, and the flux in y direction similarly. And then we get the rate of change, which is this flux, the divergence of the flux in x direction, divergence of the flux in y direction, and we have this dH by dt. We just set this divergence, and we can solve this explicitly. So this is in this code diffusion to the explicit.jl code. And yeah, this is what the solution looks like. So as it steps over time, so this is actually an animated GIF, it will slowly diffuse out. And the initial condition we choose is just a Gaussian bump in the middle of the domain. So let's have a look at the code. So I'll now switch from the browser to the code viewer. So this is the whole code to solve this problem. So we use a bunch of packages, namely plots for plotting, printf to print some statements whilst the code is running, and linear algebra, because we do some linear algebra, namely taking the norm. Although actually, maybe in the explicit one we don't use that. There's a switch here to enable or disable plotting. And then here we have some finite difference support functions. So the first one here takes an average over an area of a quantity in x direction and in y direction. And so this we'll use this to take an average of h. And this last one is in. That just basically selects the part of the domain which we actually use for computation, because the outermost grid points, they essentially contain the boundary conditions, and they will just be fixed. So we only do computation on the inner grid points, not right on the edge. So these are these helper functions, and then we have this function here, diffusion to the explicit. We define a bunch of physics constants, so the domain size, x and y, this power, which for the non-linearity of the diffusion, so this is 3, and then the total time we integrate to. So we integrate from 0 to 1. We need to discretize the problem, so we have 128 by 128 grid cells here. We have some derived numerics, so we can have the grid cell size, dx and dy, and we can make x center coordinates vectors of x and y, which we'll later use for plotting. And then we pre-allocate some arrays. So we pre-allocated an array for the flux, which is just as zeros. We pre-allocate an array for the flux in y direction. And you note that they are on the staggered grid, and only on the inside, so to speak, not on the outermost points. So that's why they are, and x is staggered in the x direction, y is staggered in the y direction. So so they're not quite square. And then the h by dt, it's again on the normal grid, but yeah, without the boundary points. So these are the pre-allocated arrays. We have initial condition h, which is this Gaussian bump. And then we take a time step. And here we need to, this time step needs to obey the CFL condition. So that condition essentially says that, well, as the quantity diffuses across the grid, you cannot take a time step bigger than how far the quantity diffuses within one time step. Because if you take a bigger step, then it kind of diffuses over several grid points, and that makes the solver explode. And then we set up here the time equals 0 and iteration equals 0 counter, and then we do the physical time loop. So as long as the time is less than the total time, we do this loop. And so first we calculate the flux in x direction, in y direction, and then we update h. So the flux in x direction, so we take we need to take this h to the power of 3. And so to do this, we need to average this h a little bit, because the flux is on the staggered grid, and so we need to average the h, which is on the unstaggered grid, onto the staggered grid. So we do this with this helper function defined up here. And then we take the diff of h, so that just along dimension 1. So that just subtracts hi minus 1, and we divide it by dx. So that gives us the gradient of h in x direction. We need to take care a little bit of the indices here to, well, make it work out all on the right sizes. And similar for the y direction. Then the rate of change is then the divergence of the flux, and the divergence we take by taking this diff again, but now of the flux here, and again by divide by dx, and the diff of the flux in y direction divide by dy. And then we do a forward Euler step. So we say that the h at time t plus delta t is the h at time t times delta t times the rate of change of x. And then we just loop, and this will produce this, well, iterate this, well, step this forward in time. So let's try it out. So this is the Julia, well, it's my bash shell, and I'll start Julia here with as a project within this project, and I'll start it with 8 threads. So at the moment we don't need threads, but later on we do. And now I just include, let's see, what's it now? Diffusion to the explicit. Diffusion to the explicit. Yeah, it'll take a bit of time to get everything loaded up, and eventually it will pop up with a plot of the final solution. Yeah, so this is this explicit solver, and yeah, it works. One thing to note is this CFL condition here. So you have to take a pretty small time step in order to make the solver not blow up. And so that's one of the limiting things, and that's what we will try and figure out in the next step. So let's just wait for Julia. Okay, so now it's solved. Yeah, so now it finished solving here. So this is the solution after 660 steps, which took us to time equal to 1. So yeah, looks good. We see here, it took 660 time steps to take us to this time 1. All right, so now, so now this, because it's an explicit scheme, we have this CFL condition which we need to obey, which looks like this. Potentially, there could also be a loss of accuracy if you use an explicit scheme for nonlinear problems. So can we use an implicit algorithm instead to ensure accuracy and also particular sidestep the CFL condition? And the important bit here, in particular for later, for GPU computing, is we want to keep it matrix-free, this method. So we don't want to be assembling any large matrices or any matrices, which you then have to, solve in some way, because that's usually not that great to do on CPUs, on GPUs. So let's move on to iterative solver. So here we have the next code we'll look at in a moment is this implicit solver. And here we do a backward Euler step. And this is done by, including the physical time derivative in the rate of change to define a residual. So we're defining this residual h here, which includes the rate of change. So this is the new h we try to find for the next time step, and this is the old h we have, and the difference with the flux here, and this is the residual, and this needs to be 0 for this time step to be fulfilled. And so how do we? So this is a nonlinear equation in h. And so how do we solve this equation? Residual needs to be equal to 0. And we can do this by iteration, but what iteration? And now we actually define a new time, a pseudo time. Let's call this pseudo time tau. And we just say the rate of change of h with respect to this pseudo time tau. Let's just say that that's the residual age. And now if we evolve h forward in time, we'll kind of reach a steady state where h doesn't evolve any longer. And so eventually when we do reach this steady state with respect to this pseudo time tau, this side of the equation will be 0. So and indeed, we then solve residual h equal to 0. And this type of iteration is known as a PCAR, or fixed point iteration. So let's have a look at what the code looks like for this. So here on the left is still the O code, the explicit code, and now here on the right I opened up the implicit code. So the top bit here, that's the same. Here the physics is the same as well, except for now we actually define a physical time step as well. Before we just defined it with the CFL condition, but now we can define it freely because we don't need to obey this CFL condition anymore. Numerics, here nx and ny is the same, the grid points, but now we need to set the tolerance for the nonlinear solver for the Picard iteration, and we need to, it's probably good to give it a maximum iteration as well, although it will not reach that many iterations. Now this is the same, and now we need to pre-allocate some additional arrays. So we have a residual h, which we pre-allocate. We have this dh by d tau, which we allocate, and we also have a d tau. This is the time step in pseudo time, and this actually can be different from one location to the other. So so we allocate the array for this as well. Initial conditions were as before, and we include a total iteration counter as well. And now the physical time loop. So before the physical time loop was this. Now the physical time loop is this. Most of it is just really the inner time loop, which is just this Picard type iteration. So we calculate here the flux. This is as before. And then we make the residual. So we take the h minus the h old. So that was from the previous time step. And h is essentially the trial for the new time step. The divergence of the flux here as the second line. And so we want to have this residual equals 0. And as we said before, we just set the dh by d tau equal to this residual. And we will step forward in pseudo time again with a forward Euler step. So now we need to have this CFL condition on tau. And then here we do this Euler step forward in time and update h. And we check, well, we increment the iteration counter, and then we calculate the error by taking this norm of the residual and divide it, well, scaled by the length. And we do this inner Picard iteration until we converge to our norm, until we converge here. And so, yeah, so that's what it does, and eventually we'll do the plotting. And so if you run this example, actually, so it ran as well, but we actually see that the iterations here are pretty large. So that was 850 iterations compared to 660 essentially iterations before. But yeah, it works. But so the question is now, can we decrease this this iteration count? And an efficient way to do this is to add damping to the pseudo time rate of change. So instead of, so before we just wrote dh by d tau is equal to the residual. But we can also, well, we just need to have dh by d tau equal to well, when that is 0, then the residual will be fulfilled. But we can actually add other stuff to the right-hand side. And we can add, in particular, we can add this damping term here. So this is a constant times the previous dh by d tau. So that's from the previous iteration, the dh by d tau. And it turns out if we actually do this, yeah, it gets much better. So let's have a look. So now I move the code you saw before from this side to the left side, and the new code of this damped iteration is now here on the right side. So it's all the same here, apart from we have this additional damping constant here. Yeah, and other than that, it's all the same, except now down here, instead of just doing dh by d tau is equal to the residual, we have dh by d tau is equal to the residual plus damp, so this is constant, times dh by d tau from the previous time step. And yeah, so that's all there is to this. Then we run it, and yeah, let's try it out. Yeah, so here it is, and the thing to note that the iteration count dropped from 800 to less than 200. Yeah, so that's great, and in fact, this pseudo-transient approach with damping is a second-order type method, and it enables that the iteration count scales close to order n, where n is the number of grid points, and not order of n squared like you do with a usual kind of Picard iteration. So this is similar to how Newton's method, for instance, scales as well. So here's a plot of how this number of iterations scales versus the number of grid points in x direction. And we see if you increase the number of grid points in x directions, the number of iterations normalized to the number of grid points in the x direction actually stabilizes to a constant, which is good. Yeah, so now we have an implicit solver, and we can actually compare as well the implicit solver with the explicit solver. To do this comparison, we actually run the implicit solver with smaller dt physical time steps, because even though the implicit solver you can take as large time step as you want because they're stable, the error incurred per time step is still linked to the size of the time step. So to have an accurate solution, you'll need to still take reasonably small time steps. And so if we take small time steps and compare the explicit versus the implicit solve, we see that there's actually a difference between the two in the front of this propagation of this nonlinear diffusion. However, arguably this 2D nonlinear diffusion problem is probably solved similarly well by either method. So either by the explicit method or by the damped implicit method. But there's other partial differential equations out there which are much stiffer, and they need an implicit time stepper to work. So as maybe for this problem, it's not 100% necessary. For other ones, you definitely need an implicit time stepper. All right, so this is kind of gave us a small overview over the basic, I guess, mathematical, numerical techniques used for the rest of this workshop. So we saw that we have the nonlinear diffusion equation, which we'll use as an example throughout this workshop. And then we saw how to solve this in an explicit fashion using finite differences as as spatial discretization, and forward Euler step as a time discretization. And then we went on to using a backward Euler time step, which is an implicit method, but that then needs a nonlinear set of equations to be solved. And this nonlinear set of equations we solved with eventually with a damped iterative method, so a pseudo-time method. And we saw that this actually scales pretty well on the order of ON. And yeah, maybe here just then as a aside, so often this, if you do implicit time stepping methods, the way to solve these nonlinear equations is usually done by Newton's method, which is another way to solve nonlinear equations. Probably there the iteration count is actually a lot smaller than with our pseudo-transient method. However, it's tricky to make them matrix-free. So the standard implementation will assemble a Jacobian matrix, which then needs to, well, solved repeatedly to solve the nonlinear equation. Yeah, so this is not a matrix-free method, at least in the simplest implementation. Whereas here we have a very simple matrix-free implementation, which we can, which we can implement. Well, if I go back to the code here, which you can implement essentially in just a very few lines of code, which is nice. So, okay, so just a side tour now to performance considerations. So efficient algorithms should minimize the time it takes to reach a solution. And so for iterative algorithms, this means keep the iteration count as low as possible and ensure fast iterations. With our pseudo-transient method, we keep the iteration count, well, pretty low. So we solved number one, and now we want to also ensure that we have fast iterations. And that's essentially what the rest of this workshop is about. And one thing to bear in mind here is that well, I think in general, most methods to solve PDEs, the bottleneck is not how quickly your CPU or GPU can perform floating point computations, but how quickly memory can be accessed. So the solver needs to access lots of memory of the grid at different points to then do whatever it does with those grid points to solve the equation. And it turns out that the bottleneck is the memory access. And so we want to express our performance in terms of memory access efficiency. So memory access can be defined with how much memory is accessed. So we can calculate this. So the effective memory access AF in gigabytes is the sum of twice the memory footprint of the unknown field. So we need to read and write those unknown fields. And once the memory footprint of the needed known fields. So that's just, well, those fields just need to be read. And so that's just a single read. So the effective memory access is this quantity. And then the effective memory throughput, T effective in gigabits per second, is then just this effective memory access divided by the time it takes for an iteration. And for our problem here, this effective memory access turns out to be around this. So it's 2 arrays which we need to read and write, and 1 array which we just need to access. Yeah, so we'll be showing this T effective in the rest of this workshop as a memory, well, as a performance measure for our algorithms. All right, so this was a short detour to how to measure performance, and now we come to part 2, and so that is the parallel CPU and GPU computing. And so I'll do the parallel CPU computing, and then I'll leave the field to the expert to do the rest of the workshop. And so as a first step, we wanna improve the performance of our diffusion 2D damp code. And we do this with a few things. We want to do this, well, we will be using broadcasting for now, and we just want to use a single line of a broadcasting statement so that there's no extra temporary arrays needed. So yeah, that way we avoid extra work arrays, and yeah, and to make this actually a bit prettier and shorter, we will be using macros for those repeated things. We'll introduce a H2 array, which holds H as well, to avoid race conditions once we parallelize the code, because different threads will be accessing H, and they all need to have kind of access to the old version of H before and write to a new version of H, so they cannot be the same. We will use a non-allocating diff operator, which from lazy arrays package. And then, yeah, we'll add this timing, and we report this effective memory throughput as a performance metric. Okay, so let's have a look at what this looks like. So this is in this diffusion 2D damp perf.jl code. So here on the left is the code you saw before. So this is diffusion 2D damp. So that was the damp pseudo-transient method here. And now on the right is some performance enhanced code here. So you see at the top we added these macros here, which are just sugar to avoid us having to write out really long lines of code. And so there's this QHX macro, which computes the flux in X direction and the flux in Y direction, similar for this. And there's the dtau macro, which computes the CFL condition for each grid point for tau. Okay, so that's the macros. And then now let's compare the function. So here at the top, that's all the same, except for the array allocations. Now we just need two arrays, namely the residual of H and the dH by dtau. And we don't need arrays for the flux, and we don't need an array for dtau. We still need an array for H, like we did before, and for H old, like we did before. And now we also add this H2 array, which actually in this code, because this isn't parallelized yet, we don't strictly need, but we just add it here as well. And then let's have a look at the loop. So this is the loop we had before. Remember, outside is the physical time loop, and then inside is the Picard type iteration, which we have damped here. And so here is the physical time loop, and here is the Picard type inner loop. And now we see that we don't actually calculate these things here. We go straight to calculating this. And so dH by dtau is equal to the difference of H minus H old divided by T. That's the backward Euler part, plus the divergence of the flux. And now we calculate it straight from all the inputs, and we use this macro we defined above to keep it short and readable, because otherwise it will be probably at least 2 lines more of code, which makes it harder to read. And we add the damping rate as well, right to this. And then we update, and we actually first write it into H2. So if we did this in parallel, this wouldn't interfere with this H. And eventually we'll just do a pointer swap to put H into H2 and vice versa. And now we need to calculate the residual at sometimes, but we only do this every so often, every n out steps, and this n out is actually defined as 100. So we only calculate the residual every 100th iteration, and then from the residual we can calculate the error, and we can terminate the iteration if the error is below our bound. But we decide that we only calculate this error every so often. And down here we added the reporting to do this T effective, so that's effective memory throughput in gigabits per second. Okay, so let's run this code. So I'll just include this code here. It always takes a little bit of time to compile, as you note, and then it should run reasonably fast. Oh, wait a second. That was... Yeah, no, it's actually not running that fast because here we increased the number of grid points from 128 to 128 to 512 by 512. And this isn't actually all that performant yet, so it actually takes a bit of time. So we'll just let this run and take the next step already. So let's come back to this once it's terminated, which will be in a few seconds. Okay. And so here in the README, actually, it will tell you the time is actually not run on my laptop, but on a different one. And so on this different one, it took 20 seconds to run, and the effective memory throughput was about 0.4 gigabits per second. So let's move on to make this a parallel CPU implementation. And this, so we take this code, it's now the loop version thereof. So instead of doing the broadcasting, we now transform this into a looped version, which we can then turn into threaded code. Okay, so now we have this performance stamp perform. We'll move it to the left. So this is the code you just saw before. And this is the same code, but now using loops. And so we don't actually need these finite difference support functions anymore. And we still keep the macros. And here the top part is all the same. But now down here, instead of doing these broadcasting operations, which we had here, we do loops. So let's just have a brief look on what this looks like. So here we calculated this dH by dτ in one swoop of a broadcasting operation. And here we step through each grid point. So IY and IX, we go from 1 to the size of dH by dτ, one dimension and the other one. And then we calculate this. And so we have H at this grid point minus H old at this grid point divided by dt. And now we have these macros here again, but we see that we actually updated the macros to take the grid points as well. So now the macros here take the grid points. And again, these macros are just used to, well, make this shorter. And yeah, so that makes it more readable. Yeah, and here the same again for the error calculation. We do this only every so often, and then we do it in a loop instead. And down here is the same. So, okay. So the previous calculation now finished, and for some reason, I guess on my computer, well, I guess I started Julia without optimization turned on. It took 40 seconds to finish, and actually the memory throughput didn't really get any better. Or no, we didn't. And the memory throughput is 0.22 gigabits per second, so that's kind of comparable. So now let's run this same code, but the loop version of it. And this should run. So this is also on the big grid, and this now runs a lot faster, about 10 times faster. And now, yeah, has 10 times larger memory throughput, namely 2 gigabits per second. Yeah. And so that's good. And now the last step here will just wrap these physics calculations, these loops, will just make separate functions for those loops, because later in the GPU computing part of the workshop, these are the GPU kernels which are needed to, well, hand over to CUDA to do the calculation. So this is getting pretty close to what the GPU code will eventually look like. And we'll actually add threads to that as well. So again, as usual, I move this code to over here and compare it to the updated code, namely the loop with the functions. So now, instead of having within this physical time loop, we have these inner loops, we just call out to functions. So we call out to update, compute update, which updates H2, and we compute residual, we just call out to this function here. And eventually we'll actually, instead of this pointer swap down, well, instead of this update from age to age old, we just actually call this function here as well. And we can have a brief look what this function look like. So the compute update is essentially just these loops here moved into a function, and we added a add threads macro in front of it, which means that these loops run in a threaded fashion. And yeah, and the same goes here for the residual and the assign. And remember, I started Julia with 8 threads, so now we should be using 8 threads as well to run these calculations. Oh, sorry about this. Yeah, so I run this this code as well. Unfortunately, we lost the screen before. So let's compare it with the one without this threaded. And we see that, yeah, we improved the performance quite a bit, from 2 gigabits per second to almost 8 gigabits per second by actually now using 8 threads. Okay, so this kind of set the stage for what the rest of the workshop will be doing, namely porting this code to the GPU. And so, yeah, so now it's time for some questions and answers, and then we'll actually take a short break as well before Ludovic will be talking about the GPU implementation next. So I don't know, Ludovic, are there any questions which we should answer here, or not really?
Yes, well, thank you, Mauro, for this very interesting first part. I was also about to ping you that, well, there may be 1 or 2 questions that could be interesting to a live answer. So I think one of the most upvoted question is that besides like our motivation in writing a solver that relies on this parallel stencil and implicit global grid for both research and teaching purpose, the question is like, how would differential equation.jl perform on the same problem? So maybe you want to say something on that, Mauro?
Yeah, so is this what's the motivation of writing your own solver instead of using existing Julia libraries? Teaching purposes, how would differential equations perform on the same problem?
Well, mostly the last part. Sam answered by text, I think, the first but if you have any thoughts, share them. Yes.
Yeah, so we're still working on or I guess we had some discussions with Chris as well on how this would work with differential equations, or potentially you could use, I mean, for the differential equations.jl, you need to spatially discretize your PDE somehow. There's a few libraries within there which allows this, but there's also, I don't think that's kind of, solved problem. And then you can use the ODE solvers from within differential equations to solve that. And I think that's probably a good way to go. I think the motivation here is that it's a bit hard to see what exactly is going on once you move all of this to the GPU, on whether this can all be done on the GPU or not. And the nice thing about this pseudo-transient method that is really simple, and we're confident that it just runs on the GPU fine. Whereas, as I said, the differential equations.jl will be using Newton's method, so that involves a lot more machinery to get going. So you then need to first figure out how to calculate your Jacobian. So that involves finding out the sparsity pattern of the Jacobian, then calculating the Jacobian with some automatic differentiation tools. And then once you have that, you can plug it into the nonlinear solver there. And we're not quite sure whether this all works within the GPU framework which we have set up here, or as Ludovic just posted a comment, there's some discussions on this in a parallel stencil issue number 31. So I hope this at least semi-answers the question.
Yeah, thank you, Mauro. I think it's kind of nice, interesting insights, and as you say, like, I think the one current things that could be exciting is to see if we can use, like, combine some functionalities of DFEC and parallel stencil, like leverage GPU or multi-GPU, and then have like the ability to perform like to get some gradients or things like that from differential equations. So, but I think there's some, like we saw in the workshop from on GPU computing, I think the first workshop where Tim Bazar was discussing some of the challenges related to GPU kernels, and that everything there has to be very static and very well known in advance. So I think there's some iteration needed in making, for example, if we want to try to make these two packages to talk together and like to work for both, like maybe making automatic differentiation and things like that. There's a bit more work needed, but that's definitely something that could be interesting, like in the future. So just checking quickly what are the status on the most important, like, upvoted question. I think we're pretty good. I hope like that there should be like answers, written answers for all of the questions in Pigeonhole right now. Maybe I can.
There is this one with 5 votes without automated differentiation. What does the process look like for solving this equation problem? And the thing is, this pseudo-transient Picard type iteration doesn't need automated differentiation because we don't need to calculate the Jacobian and whatnot. So this is what makes this method nice, because it makes it much simpler than the Newton method, which where you need a Jacobian and you need to somehow solve the matrix equation then and whatnot. And this is just a matrix-free method by design. So that makes it easy.
Yeah, and that's a good point. And maybe just a quick quick comment to, since it was a question as well about the matrix free. So yeah, in order not, there is could be confusion around all this terminology that's sometimes specific also to different parts of domain science that has different names for different things. But yeah, to just totally clear, like what we call here matrix free is matrix free solvers. So like for sure, like let's say here in the example, we solve for H, which could be like height of ice distribution, for example. And this is still stored in a 2D array, like a 2D matrix. And there we leverage the performance of the GPU to process these 2D matrices that are dense, because it's just like 2D field that maps to the 2D physical fields. And we update this like iteratively in every grid point, in every iteration. This is very different from a matrix-based solver, where let's say one could have it matrix, like the standard matrix-free solver would be like, when we discretize the problem, we build a coefficient matrix, which results in a sparse matrix that's much bigger than the number of grid points you have in your domain. And then, one does operation on that matrix, like one tries to invert it or to approximate an inverse. This is like what is called a matrix-based solver or matrix-based solving method. So just to be clear about one and the other. And the drawback of the matrix-based solvers are that if one really handles them as matrices, well, then your sparse matrix, coefficient matrix, its size would grow nonlinearly with problem size. And when you try to find an inversion or invert it, then you would also get like a lot of non-zero entries, and all this like would congestion the memory with more and more memory traffic. And so you won't scale like with growing resolution. So just to be clear on that.
Yeah, but I think there's non-matrix-free solvers for doing Newton method as well. So yes, they're around and they are good, but they're also a lot more complicated than this method. Yeah. So
yes, that's correct. So yeah, I would suggest we make like truly a couple of minutes of break until I take over for making the shift towards the GPU. So yeah, let's be back in 5 minutes. So here we are again for the next chapter of that workshop, which is about GPU and GPU implementation. So let me share my screen. Yeah, so as Mauro just ended, so the last code we were looking at was the diffusion 2D that had a loop version in function where multi-threading was enabled. So maybe this will be my screen now, so that you get used to the same. So the code here in full screen, and if needed, visualization and terminal will be on the right. So yeah. So the best one can do in the kind of CPU code, stencil code, would be to have this double loop over spatial indices or spatial dimensions like ix and iy. And this was also a question in Pigeonhole. Like I think this is pretty standard. Like if one wants to parallelize this kind of approach, well, what's standardly done is that one would parallelize the outer loop. This is just like otherwise, but otherwise you get race conditions and other things, like because this just would split now the outer loop on, let's say, how many threads, and the inner loop will still be totally independent. So that's kind of standard way to go. Yeah. So now the idea is that we will port this code to GPU computing. So maybe a couple of reasons why to go to GPU computing. Well, it's mainly performance, and performance can have, like, there are two aspects on that. So either you have a code or that solves a given physical problem, and you already run it at quite high resolution, but you want to run it faster, or you have a kind of code that you want to run at much higher resolution, and you would also need some more parallelism at the end, because, well, the thing is, if you take a CPU like that's here, so they have, although recent CPUs or modern CPU, they have a couple of cores and up to many cores, like I think now one can go 64 or even 128. Still, one would say a GPU has like much more cores. The most important, however, since like maybe to go back to the metric we introduced, like what's really key for us are for when writing efficient iterative type of solvers is the memory bandwidth. So CPUs, they have a lower memory bandwidth than GPUs. And that's really the key. So that's why GPUs, at least for us in our framework, are faster, is that, well, GPU have much more cores, they can launch much more threads, and all this increase in number of parallel worker, what it will turn out at the end of the day is that you will be able to generate a much larger memory bandwidth. So basically the pipe between the computing units and the main memory is much thicker. And this is why our codes who are like memory bounded go much faster on the GPU than on the CPU, or that's the motivation. So now in the first, we'll continue our incremental kind of development. And so the first step will be to take this loop code that was written in where the compute functions were explicitly like kind of written in functions, and turn this CPU code into a GPU code using the CUDA.jl, which is the NVIDIA GPU backend of like available in the Julia ecosystem. And so one of the motivation also since the beginning of that workshop, and here I will also continue to stick to that, is that, well, the idea is to have the kind of minimize the number of lines of code, and also between the steps try to really keep things to the minimal amount of changes, like just as general approach, like the less work, the less lines one has to do, the less things can go wrong, the less performance killer can hide. So just as a overall motivation. So the main thing that will happen is that on the GPU, we now have much more cores, but especially we have access to much more threads. So if we look at the schematic on the CPU, we may have a couple of cores where we can launch a couple of threads, a factor 2 if one use hyperthreading. On the GPU, we have like thousands of cores, and one can launch tens of thousands of threads. And each thread is a separate parallel. Well, all the threads now can really execute the same task, but in parallel. So you can see it like a nice analogy is if you imagine that you have a potato field and you have to harvest that potato field. Well, on a CPU, you may have like two farmers that can harvest it, and then, well, they would split up the field and say, well, I do I harvest like my potatoes in lines on half of the field, and the other farmer harvests it on the other half of the field. Now one can say, well, if I have more threads or more cores, like here it's not really important, well, I can have more farmers, and each farmer would do another chunk of that field. And then in the extreme case, or what we want to achieve on the GPU, is that we have so many workers, like so many farmers, that basically we can have as much as farmers as, let's say, potatoes to harvest. And then, well, we can just send out to the field as many farmers as potato. And in the cost of only picking up one potato, we harvested the entire field. That's really the aim of how we use the GPU, and how we want to achieve parallelization on the GPU. And the way to do so is that basically there's only one single but important conceptual change, is that we'll replace our double loop over IX and IY for the spatial dimension. We'll replace it by a vectorized thread index that's spelled out as such. So it's a unique index that will be assigned to specifically to every thread on the GPU will have a different index. And so we will launch as many threads on the GPU as we have grid cell to compute. And then if we execute the GPU code, the aim is that, well, the same code will be sent to all the different threads. Every thread has a different ID, which is responsible to compute another grid point in our spatial domain. And so in one execution, basically, we can compute or update our entire array in parallel. So let's see how we can do so. I may zoom in the code. So if we take here our CPU code, and then let me split it with the GPU code on the right. So the setup now is on the left of the screen. We have the most optimal CPU code we discussed, and then on the right we have the GPU code. So the main changes that occur here is the first, we have to use the CUDA package. So here again, big shout out to Team Bazaar and the team on Julia GPU for the really performant CUDA wrapper they provide. Next, so this macro or syntax sugar, they remain untouched. And so really the only main difference is here you can see in the loop version, we had in the function defined, we compute over a double loop over the spatial indices our array. And in the GPU code, we actually can remove those loops and just assign thread index IX, IY. And those block ID, block dim, and thread ID, those are variables that are received from running this on with CUDA. So that's the only and unique important change conceptually that we do. There's one thing that we have to care now is when we did the loop version, like it was, well, then when you do a loop, you can control your bounds with the loop. I say, well, I can loop from 1 to a given size because I know the size of my arrays, and I can thus ensure that I kind of loop through the entire array without going over or missing some lines or columns. With the GPU, it's a bit different since the GPU function here, or the compute function, which is usually called the kernel on GPU computing, will be the same function will be kind of sent to every thread. So everyone will read the same code and has to come up with a different bound checking. And here we do the bound checking with an if statement. So, well, every thread or parallel worker will receive that function, will check if he knows, he has an unique index that's specified, I, X, I, Y, and it will check if this index basically has to participate or not to the computation. If so, he will execute a specific point of this calculation. If not, it will just stay idle. And then we return from the function. So that's the first and really big change. If I go now further down to the main, there the kind of what remains now to do is, well, we have to somehow initialize or define what are these block grids for the GPU calculation, and launch our compute function with some keyword arguments, because with some macros or some specific arguments that this will run on the GPU accordingly. So the important thing here is that one has to really map the number of threads one use with the number of grid points to compute. Now you can imagine if I launch 1,000 threads, but I only compute 500 grid points, well, there would be 500 threads or worker that would be idle. And this is kind of not good for performance. So the easiest way, and the way we decide to do this, is that we select kind of the right amount of worker that would also kind of deliver good performance on the GPU, and then map or define our numerical our number of grid points accordingly. So this block and this block X and block Y are the elementary blocks. It defines the elementary number of threads in a block, and then grid X and grid Y defines how many times we repeat these blocks. And here, Tim made a very, very in-depth and good introduction, I think, on these concepts on the Monday, like on the first workshop. So I will refer to that if you want more insight. So here we define now the number of grid points as function like to map the number of parallel worker. And so then the remaining changes would be that for sure now our array, they're no longer CPU arrays. We use CUDA.0, which will initialize a GPU array of float 64. The default arrays on the GPU are float 32. So one has to kind of be explicit here that for comparison purpose, I wanted float 64. My initial condition, I can still initialize it as if I was doing this on the CPU. I can just wrap it on this Q array. So this would then copy it to the GPU. And then I have to build what's called this Q threads and Q blocks tuple that will then be later passed to the kernel launch. So how I can now, this was my CPU function, compute update. And now to make it run on the GPU with the given number of threads and the given number of blocks, I can use the CUDA macro and pass the block size and thread size, and then the compute function, which is somehow, like the arguments here aren't changed. Important point here is synchronization. So we do here spatial derivatives. So this the calculation in the compute update function, they rely on neighboring values. So one has, since now you can see the point that now I execute or I update H on every grid point by a different worker in parallel. At some point, I have to ensure synchronization, because if I don't, well, then nothing guarantees me that actually I'm still reading from the current neighbor value and updating to the new value. I mean, if there is some drift occurring, then I could also start to read from already updated values, and then you get some non-synchronization in your execution. So this is very important. Like, one need to synchronize the GPU after each kernel call in order to be sure that, well, I always read from the current value to make the update and then write to the new value. And then again, here we can use that common trick that, well, although with synchronization, I need to read from, I have this temporary H2 array, and then I make the pointer swap so that, well, each time I kind of read from one place and write in another bucket, then swap the pointers, and then this avoids, like, pointer swap here doesn't cost any time, while if I had like literally two arrays that I exchange, well, depending on how the compiler optimized things, I may have like memory traffic that's generated for and not really used. Yeah, that's it. There are no other changes in the code, so I think this section of the README provides or highlights the only changes to get our fully working GPU code. And yeah, here I made some little disclaimer just to be sure that that everyone is on par. So enough talking. Let's see how the GPU code performs. To do so, I will run it on a GPU. So I am here already. I have already started my Julia REPL, and maybe important, I started it with the -03 optimization flag, and I deactivated bound checking. So it's kind of the similar as having at inbounds condition. This is like for then you get optimal performance. However, when you make the development, one shouldn't disable the bound checking, because, well, then you don't get warnings if you kind of mess up ranges basically of the arrays. So I can now include this 2D damped performance-oriented GPU code, and I'm running it here on a NVIDIA Tesla V100 PCI Express 16 gigabyte card. So it takes a while because I'm running it at quite high resolution. So I'm running it at where is my GPU code? Sorry. So I'm running it at 8,192 times 8,192 number of grid points. This is needed because since the GPU has a much larger memory bandwidth, one needs to get the full performance of the GPU, one has to saturate it. Like, imagine if you have a highway with 5 or 6 lanes versus a highway with 2 lanes. In order to get like the full traffic on the highway with 6 lanes, you need much more cars to go through per amount of time. This is why we have to increase the number of grid points to get the relevant performance measure. I'll come back in a while also on this performance measure, because I did some systematic that you can try to reproduce. That's material is all in the repository. So Well, here we are running the code on this. So running the code on 8,000 grid points times 8,000 grid points for the same problems from the same configuration we were looking at since the beginning. Took 10 seconds, and the effective memory throughput is 780 gigabytes per second. So if we go back to the result we had with the for multi-threaded loop performance, we were at 8.8 gigabyte per second. And the CPU here I use had about 25 gigabyte per second of peak memory throughput, which is we were at between 1/3 and 1/2. Now with the GPU code, we are actually at 780 gigabyte per second, knowing that this Tesla GPU has 840 gigabyte per second as a peak performance. I'm just checking one thing. Okay, what it takes. Okay. Yeah, so that's cool. I mean, we kind of we're very close to the peak. We're very close to 840 gigabyte per second, and 840 gigabyte per second. Yeah, maybe the peak performance is really it's just copying memory. So basically, I think we lost about 7 or 8% performance from solving a nonlinear diffusion equation versus just copying memory around and not doing any calculations. So that's great. However, well, now we have somehow introduced what I call, or what one could call, the two-language problem. So we have a CPU code that uses some fancy multi-threading that works great on the CPU, that leverage kind of a good part of the memory bandwidth the CPU can deliver. And then we have a GPU code that runs super great and that leverage nicely the GPU. But then it's the kind of these two-language problems. So maybe my development configuration, my laptop, my little cluster has no GPU available, or I want to run interactively some things, and then make some little debugging on the airplane, in the train with my students. And then, well, once I'm happy with my new physics, I added some fancy surface processes. Well, then I want to make some high resolution run, now not on my benchmark problem, but maybe on Antarctica or Greenland, and I need high resolution, or I have a supercomputer that has GPUs and want to use them. And then, well, in general, if I have several codes, then, well, there is always time needed to go from one to the other. One introduces errors while doing manual typing. So the cool idea there, or to solve this two-language problem, is it would be great to have a single code that does both. And so the single code, or the approach to solve this two-language problem and have a single code that does both, is to use parallel stencil. So parallel stencil is a package developed by Sam and myself that permits to have this backend agnostic implementation to run on what we call XPUs that would range from CPUs to GPUs from now on, but yeah, potentially to other parallel devices if suitable. And so as next step, what I will do is I will show how we can write the GPU code we just got in a XPU to get this XPU code, and then the entire point of making this step is that one can now have a single flag that's called use GPU that I can switch from true to false without changing anything else in my code. And then I will have a code that can run on mid-resolution on my little laptop in a local Julia install, but this exact same code kind of can be launched with whatever the most advanced thing like CUDA or MPI to run on an entire GPU supercomputer. And so like again here, this little in the README, this recap will kind of highlight the couple of changes that are required. But let's switch to the code to do so. Yeah. So now we'll make side by side the XPU and the GPU codes to show you like the most important differences. So in the XPU code, well, we have this use GPU flag that can be set to true or false, depending if one wants to, if the GPU flag is true, it uses the CUDA backend on the given precision in the given number of dimension. If the use GPU flag is false, it would initialize parallel stencil on the threads backend, so the base threads backend on the given precision and given number of dimensions here too. The rest is unchanged. I can still have my syntax sugar for non-allocating assignments. And so now maybe the most important thing is here is that, well, now my function compute update that was defined as just as a function here gets some additions, which is parallel indices macro that takes my 2D spatial indexes ix, iy as input. The rest is unchanged, just that, well, now I can kick out these ix and iy definition or explicit definition within the compute kernel, because now this is implicitly handled by parallel stencil under the hood. And so basically what parallel stencil in a nutshell will do, parallel stencil will analyze that code and will kind of paste in this threaded block and thread index if we use the GPU backend, or it will nest these statements within a multi-threaded double loop in 2D or triple loop in 3D if one selects the thread or CPU backend. Well, that's it. So then if we go down to the, if we go further down to the main, no big changes. The only change is, well, that now again, parallel stencil will handle automatically for us that, well, now we give at parallel macro, define or have to pass the block size and thread size. And then, yeah, then we can, as such, launch the compute, the kernel function. And the rest of the code is unchanged. So now the idea is really that this code should perform at the same performance than the, like, somehow, let's call it CUDA.jl native or natively written GPU code, but would allow now just upon changing that flag to go from the CPU execution to the GPU execution. Yeah, maybe one thing that can be also noted is that the array initialization now takes an at 0. So there's these macro zeros that would also switch the, like, implement the correct initialization depending on the backend and the wrapping. So if you have a, let's say, a CPU initialization that you want to copy to a GPU array, well, now we can use the data array type that will make the port, like make H being a GPU array. So running this code, I don't know where my thing crashed here. Just have a GPU issue. Let's switch to another GPU then. So if I run now the diffusion to the dump which is per XPU. So now if I run this XPU code, it will take a little moment to run it, but then we should get like very similar performance than the native CUDA code. So let's launch this one so I can see if I'll run it on that GPU as well, just we get the performance comparison. Yeah, I know what was not. So yeah, since we're just taking a while because it was trying to make the visualization, and since the resolution is quite high, I think it's the plotting pipeline that struggles a bit to get the visualization done. So let's deactivate visualization as it should have been. So just as a recall, the native GPU code was running at about 770 or 780 gigs per second, and then we'll directly switch to the XPU code, just so we have the comparison and running it on the same GPU. So this was 780 for the GPU code, and now if I run the XPU code on the GPU backend, I should get about 770 or 780 gigs per second as well. So let's wait until this result arrives, and then we'll move on to see how we could maybe further polish a bit the code, like using other features from Parallel Stencil. So there is a little difference in the performance, and this is due to some automatic range detection that goes on in the XPU code. But yeah, so this will be fixed in the next release of Parallel Stencil shortly after the workshop. We just didn't manage to finalize it for today. But basically, it's kind of very, like, it's less than 1% modifications in the code. I ran the wrong code actually, so I think the XPU2 implemented the latest changes. Yeah, and maybe you are wondering why there are warnings. So these warnings, they're absolutely not harmful. It's just like to warn the user that, well, if one uses Parallel, one may want, it will like redefine the data type and the backend, and just like, if this occurs at the beginning of the script is okay, but one cannot flip or change like data type or change backend within the script. It's not the meant utilization of Parallel Stencil. It is why it emits a warning when it runs, when you rerun it like interactively. But that's great. So basically we get the same performance. So 770 gigs for the XPU version that can now automatically switch from GPU to CPU versus the native or Julia native GPU implementation of this diffusion code. So that's it. There is maybe one comment I can make at that point, is that if one wants to have a more like a nicer written or a bit more syntax sugar with Parallel Stencil, this is why it was developed for. And then you can basically in Parallel Stencil, you can have submodule that allow for math close notation in kernels. And here, for example, I would use the finite difference 2D module. So for now, we have like only finite difference modules, so the 1D, 2D, and 3D. And what is finite difference module provides? They provide support function to do standard stencil operations. So I would have now the ability to do the averaging in the x direction of my array H without having to explicitly type it or type that formula to do the averaging, but it would do it for me using that macro. The same for the differentiation rules. They can be directly used with this diff or dxy. This would mean like, well, I take the derivative in the x direction, the first derivative in the x direction, and I take only the inner point in the other directions. And yeah. The thing is that, well, with this implementation, for now, it doesn't allow to make non-assigning macros. So I have, I cannot like directly add these calculations within the QHX definition, for example, here, because this would mean that I have a macro that does differentiation that's called within another macro that does differentiation. And for now, we don't support this. So since this is not working or not supported yet, we have to explicitly define, for example, the flux calculation in our case here. The time stepper can be done with a macro because there is no other operation like the differentiation that occurs on that d tau array. So I can make a macro. I cannot make a macro with the QHX, for example, because I have differentiation of H in this QHX, and then I need to differentiate QHX another time. But the thing is, and this is also like to point out, especially on the GPU, why memory transfer matters and why one should avoid them as much as possible, like these temporary working arrays. So you see, only by introducing these two additional arrays, QHX and QHY, I get my performance that drops from 770 gigs per second to 360 gigs per second. So basically, there's a factor 2 difference just because now I have more memory traffic. Like for solving the same problem, I allocate QHX and QHY, and every iteration I have to write these things to these arrays and read from these arrays here. While in the optimized code, well, I just directly read H in like every other places here. So this is why really this emphasis maybe was not clear at the beginning, like why it's important to not make like temporary storing of arrays that don't have a history, that don't need update. But here you see that this has like major performance impact. Well, before we like to end this second part, and before we move to distributed computing, I want to show you some performance and scaling that I did with the different codes, basically CPU code and GPU code. And I kind of on purpose made two different plots because, well, the scale is quite different. Otherwise, one just doesn't see properly what's going on there. And the log plot is also not really nice. Doesn't show nice behavior here. So what I did here is I looked like in terms of this effective memory throughput that we were using since the beginning, how this effective memory throughput would evolve with increasing number of like grid points. So the idea here, it's called the weak scaling. So we are not interested in the wall time. We're not interested in how many iterations we do. We're just interested in seeing for a given number of iteration or a fixed amount of work, how the effective memory throughput evolves while changing the number of grid points. And the number of grid points here, it's always the number of grid points in one direction. So this would be nx, which means like this 2048 means 2048 means that, well, I have nx equal to 2048 and ny equal to 2048. And so the 3 codes tested here on my i5 Intel i5 CPU with 4 cores is the like standard vectorized broadcasting Julia implementation that runs at about 0.4 gigs per second, which is basically single-threaded, more about single-threaded C execution. So it's like totally what's to be expected. Then there is the loop function that runs a bit better. And there, like, as Mauro said, we need to further investigate. I mean, if there is interest, one could further investigate what's the difference there. Like, I don't know if having loops like permits to Julia under the hood to make like further optimization. Yeah, this is not kind of really in the scope here. And then like the loop version with functions and multi-threading. Maybe multi-threading is the most important here. While we get up to this like 8.8 gigs per second, which is kind of also to be expected. Is about, I had 4 cores, so it's about 4 times this performance, so everything is fine. However, well, it's about in the range of 10 gigs per second. And then now if we go to the GPUs, here is how it looks like. So also maybe notice that for the GPU, I included larger size for the reason that, well, the memory bandwidth is larger, the peak memory bandwidth is larger, so I need more work to saturate the GPU, basically. And so we see that the besides the standard or the math close notation parallel stencil implementation that runs about at half of the other. The most important is that parallel stencil, if one wants the performance optimized one, it runs as optimal as the Julia native CUDA.jl version, like the Julia native version that relies on CUDA.jl. And yeah, and this for the entire range. So we see that about 4,096 grid points in X and Y dimension, we saturate the memory bandwidth. And as I wrote it here, the memory throughput we achieve, like solving a real world nonlinear diffusion equation, is about 92% of the peak memory throughput of the GPU. And remember that the peak memory throughput of the GPU is really what it, like how efficient you can just shuffle memory around. So basically it's the upper bound, like you cannot go faster than just sending memory around. So I think this is really a great result. And this is somehow what drives, also to answer some of the questions from Pigeonhole from the first part, this is really what drives the development of parallel stencil, because it's really focused to be able to leverage nearly like the peak performance of the processing capabilities of the GPU. So that's it for that second part, which was like to show how little changes, with how little changes one can do like a top performing GPU code. And yeah, maybe recall that, I mean, either both like the parallel stencil code and even the just Julia CUDA.jl native code, like this is really the entire code. So in terms of lines of code, like there are 100 lines of code in both codes. And this code, like parallel stenciling 100 lines of codes, is a fully CPU or GPU parallel code that solves nonlinear diffusion equation in 2D and produces that figure. The same for the GPU code. So yeah, I think I'm more or less done for this part. I don't know if there's some pressing question on Pigeonhole we could answer in the next couple of 5 minutes, and then we make again like a real 5-minute breaks.
Yeah, maybe there's a couple of questions you could try and answer. Let's see. One of them was about kernel abstractions. So the question is, what's the difference between parallel stencil and kernel abstractions.jl? Do you want to have a go at that?
That's a good question. Maybe I was wondering if Sam wants to jump in on that one.
Sure. Hello, you hear me?
Yes.
Okay, I was just typing an answer at the moment. Yeah, so kernel abstractions is comparable to like CUDA.jl or IMD.jl, operating at a very low level. So to do really performant code, you need to really know what you're doing, right? You need to be quite an expert in that. And so I would say it's rather destined to, well, destined is maybe not English. It's rather, the target group is rather computer scientists to write the code, I would say. While parallel stencil plays on a much higher level, it tries to directly be accessible to the domain scientist to make it really easy to write performant code. Of course, now everything has its advantages and disadvantages, right? So with kernel abstractions, you can do probably whatever you want, whatever you need, because you can control absolutely everything. With parallel stencil, you can do what has been foreseen more or less to do, even though, as you see, maybe with parallel indices, you can also do quite anything that comes into your mind. But let's say no, it's not yet so. It doesn't allow you to take low-level control of everything because it's not the target. And to give the final answer, kind of, kernel abstraction actually we plan to make it to go underneath parallel stencil as a backend, so that you see how these different packages stand towards each other. So the idea is really you have parallel stencil and kernel abstraction below, but you, the user, will not have to write kernel abstraction code yourself, except maybe later there will be the possibility to also give, in certain cases, the option, right? I hope that was clear.
I think that ties in a little bit with one of the another question is, which is namely, do you think that in the foreseeable future there is a chance to execute Julia code in a GPU manufacturer agnostic way? In other words, to execute the same code on NVIDIA, AMD, and Intel GPUs. And if I understand correctly, that might be possible via the kernel abstraction.
Yes, exactly. We target to add other backends like AMD GPU and also kernel abstraction as a backend. And with adding kernel abstractions as a backend, we will automatically be able to target anything that kernel abstractions allows.
Yeah, that's thanks for the precision, Sam. I think that's an important point indeed. So for sure, like now, also the demo here is all done with based on the CPU backend, but the GPU backend mainly uses CUDA.jl because it's the most mature GPU package, and it's also what we did like the first, like all the development on. But yeah, in the near future, for sure, there will be, like, the idea is really to add a support for different backends. That's really the main motivation. I mean, as long as these accelerators would somehow follow the same model of like functioning or how they work, then it could be it could make a nice ecosystem together. Yeah, so I don't know if there's another important question to.
One question I think which came up twice, if we still have time, is whether this would work on unstructured grids as well. So I think maybe just a few words on that could be useful.
So yeah, maybe, I think Sam may also. Oh, you want to start, Sam?
Yeah, just short answer. So as I mentioned before, parallel indices gives you kind of pretty explicit way to write stuff. So there you can do probably a lot. We have not done ourselves anything like that, so we cannot tell you how easy it will be, but you can do pretty much anything, I would guess, that comes to your mind. But yeah, that's what I can say so far.
Yeah, I mean, maybe just from the more domain science, I think the one thing that maybe a bit more that one needs to take care if the mesh gets unstructured is like if it's a static unstructured mesh, then it's okay. It may get tricky. Well, if it gets unstructured, distorted, and evolving, then well, there might be some challenges regarding performance if one has to if the memory stops getting contiguous and things that come if you have to remesh or things like that. So I think there are good features with unstructured grid, and there are also some other challenges because things are less regular, less straightforward to if we really look at getting the peak performance. So that may be technical challenges that would need some investigation as well.
Okay, should we take a 5-minute break and then be back here, I guess, in 5 minutes time. So see you in a bit.
See you.
You go.
So here we are again. Oops, where is my screen? Oh, I have to stream. Good. Sorry for that. Let's, yeah. So now let's dive for this last part of the workshop, part 3. Let's have a look at distributed computing, or maybe, yeah, some interesting features of how we can now leverage multi-CPUs and multi-GPUs. So in the, maybe just to make a quick zoom out and have again the broader picture of what we do and where we are. So we saw in the first part that, well, there is a way to get iterative algorithms that kind of would minimize the memory bandwidth or pressure on the memory bandwidth. So that would be, there's a scheme to reach a solution of partial differential equation that uses really minimalistic features, and would also imply like as small as possible pressure on the memory bandwidth. And this is this kind of second order iterative scheme, or enhanced or damped Picard type of iterations. And this really shows that, well, if we have the good parameters, we can keep the iteration count, not go crazy with increasing the number of grid points and the numerical grid resolution. The second important point is like, well, now we have an algorithm that scales well in terms of number of iteration, is that, well, we need also that algorithm to, or the codes that implement that algorithm to perform optimally on given hardware, like both CPU or GPUs. And well, here we had specific focus on the GPUs, just because the GPU in that sense has much larger memory bandwidth, and which means like, well, for like a relatively big problem size, it would be much more efficient to solve the problem. But then there are like, for sure, new limitations that rise. And those limitations would be like, well, what if like the GPUs, they're like discrete, at least for now, they're discrete pieces of hardware, like, or boards that are plugged in onto the main the motherboard, onto the main computer, like as you have like CPUs or memory or drives. So the GPU has its own dedicated memory, and this memory is not infinite, or compared to the host or main memory, like the RAM of the computer. Well, now we get like fat nodes with 1024 or even 2048 gigabyte of RAM. The GPU, the largest GPUs now from NVIDIA, for example, they have like 80 gigabytes of RAM, and like the usual one are more like still around 16, 32, or 40 gigabytes of RAM. And so this is a limitation, because, well, on that specific GPU, you can only solve a problem that would fit in the GPU main memory. Well, you could solve a bigger problem, but then, well, it would start to become like, you would start to have to make some chunks of your big problem and make it then more serial. But this is definitely not a path we will discuss here and we want to follow. So what can you do if you have a problem that does not fit, or does no longer fit in your single GPU? Well, one could try to use multiple GPUs and like try to like implement the concept of distributed computing that works also like for now many times with CPUs, like where you have a cluster with different nodes, different CPUs. Well, if you want to use these parallel resources, well, maybe the straightforward thing to do is you have your global domain that you cut in local subdomains, and you compute each of these local subdomains on a different computer, like this computer or hardware could be like CPUs or physically separated computer, but could also, but here we'll see or I focus on solving on physically different GPUs. These GPUs, they could be either in a same computer node, but still different GPUs, and or in spread along different compute nodes, and like could be like GPU-based, GPU-accelerated supercomputers where you have like thousands of nodes, and these thousands of nodes have either each one or 4 or 8 or 16 GPUs, which really gets you now to the, or this is really what brings us to the exascale. So in this last part of the workshop, we'll kind of explore what I call these multi-XPU capabilities. Because like now the idea is that we're convinced that we have a XPU code using parallel stencil that works great, that we can solve with this two-language problem that works for prototyping interactively on CPU or on like your small laptop. And then with changing one flag, one can run this on GPU, on a single GPU, let's say on a server somewhere, and like automatically save a GIF or do in situ visualization. So that's really what we have. And now the last step would be to enable to use this code that you just wrote using parallel stencil that would like enable it to run on multiple GPUs. And to do so, we basically rely on MPI and Julia wrapper for MPI, MPI.jl. And we'll not directly use or natively use MPI, but we use MPI via another package that's called Implicit Global Grid, and I'll come to this a bit later on. That again, a bit in the same philosophy than parallel stencil. The idea is to write to expose to the user like only a very limited set of great functionalities that enable this multi-XPU parallelization. But maybe I thought it would be good to make a short walk through distributed memory computing, starting with fake parallelization, just to well, maybe to have like everyone online with what we want or what we try to achieve, and then I will present you the tool. So the first code we look at is this diffusion 1D code that's called 2prox for 2 processors. And the idea of that, or what happens in that code, we solve the linear diffusion equation, but here without like real parallelization. I call it fake parallelization because we just, for the proof of concept, implement 2 separate domains, the left domain and the right domain. And this is shown here. So there will be an h, our height on the left, and the h of the right. And then we want, for sure, what we want to do, we want to have retrieve a global picture, h, that combines h left and h right. And I just use that small example to show you that there is one important thing when doing this distributed memory parallelization is like one has to handle boundaries exchange. So if we go to the code and look at it, so we have this diffusion 1D 2 processor code that, well, I initialize a left height, a height on the right. Then my numerical parameters, so I have a local grid point number that's 32. I have my numerical parameters, and then my initial condition, which is like, okay, I assign h left to the left and h right to the right part of my domain. And here I just copy also the global h for comparison purpose. And then on the algorithm, like solving explicitly here my diffusion physics, well, I do it separately on the left and on the right part of my domain. And then I have to do something with the boundaries and then retrieve my global picture. And then for comparison purpose, I also check with computing my physics globally. So not trying to cut it into two. So first, let's reactivate visualization. And then if I run my code, this is what I get. So I see that now, well, I had a step function as initial condition. On the left side of the domain, it's 10. On the right side, it was 1. And then if I run the diffusion, having this boundary condition fixed, I will start to get towards a straight line. And so here, all the magic happens in these update boundaries, because if I don't update my boundaries properly, then I get some weird artifacts. So that's it for the this fake parallelization, and that's exactly the concept that will occur here. So what we'll do on the idea of the GPU code we will look at is that, well, we will compute, let's say, this left and this right domain on a different GPU. And then what we'll have to take care is that over the iteration, we have to, for the local domains, so this split, this left and right is what I call the local domain. What's important there that I will have to correctly update my local boundary conditions such that each of the local domains doesn't feel that, well, it's isolated from the neighbor. Like if I didn't do distributed memory parallelization, well, if I reach the end of my local domain, it would just get naturally the next value from the same shared memory. Since I'm not doing this have access to that memory, I need to basically get an email or receive a message that ships me this boundary information from the neighboring process. Well, this was for 2 processors in 1D. Then, well, here is an example code that does it, that generalizes this for n processes. That's the nprox code. And basically, here it's a bit more, it's less hard coded. So, well, now I can, if I run that code, it should solve the same, should solve the diffusion equation again, but now just with a Gaussian initial condition. And here maybe, yeah, just for the important steps that, well, now I can control how many processes I want to mimic. So here I had 4, number of grid points. This is for local. And then, well, what will occur or what we'll have to take care is that basically for initial condition and visualization, I need some global information. So let's say I have 4 processes that each have 32 number of grid points. Well, from these, I can derive my global number of grid points, and then I can get a global grid spacing. And then I need for sure, like all my physics needs to be defined, like for example, here the CFL condition needs to be defined upon the global grid, because the Lx is my global length. And so on. And then here again, I make a loop over my number of processes, but basically the only difference with true MPI is that, well, MPI would take care of this loop, and then I will have only to write my code that's inside those loops because, well, and without this index for the process ID, because this will be handled by MPI. And yeah. So here we see that for the global initialization, I need to, so I have my global grid spacing, my Lx is my total or global domain length, which is 10 as on the plot. However, my Ix and Nx, those are on purpose local indexes, because this is also what will be available to each of the parallel processes, because, and then, well, we can use these local information to reconstruct a global index, for example, for initialization, such that I have one Gaussian that spreads over my 4 chunks of the domain, and not 4 Gaussian that would be like initializing it only with local coordinates. Here, the important thing again is that my physics, they're computed locally. So H, they're local arrays. Here it's just like over IP, which are my number of fake parallel processes. But the important thing is that this 1D problem now is a 2D array, and each of the columns of that array, or the second dimension of that array, are my fake MPI processes. And then the important thing here is the update boundary. So in my boundary update, if I screw things up, so if I don't do any boundary update here, yes, I don't think the code somehow, for some reason, doesn't get updated. Yeah, so that's nice. Just give me 1 sec. I need to run it on the. Okay. So let me, sorry for that, I was running on the wrong directory. So now it will just take some time to pop up the first plot, but basically I will just show you like that, well, the boundary update is needs to be done in a proper way. So yeah, this is what basically what happens if I now I kind of removed that. So this is what happens if I comment or remove the boundary update, and now with having the boundary update inside, it makes like the proper thing. Because what happens with the boundary update, or just what's tricky point, so basically we need an overlap of the local domains. And so you see that in my diffusion equation, basically I can only update the inner point in my local domain, because I need boundary condition. And this would be, so if on the global grid, I need my physical boundary condition, that would be my global boundary condition. Like, do I have a heat influx? Do I have a fixed heat or a fixed height? Or do I have like water influx, ice influx? Those are what needs to be coded on those boundaries. And well, on the local boundaries, we don't have a physical boundary condition because we artificially cut our domain. So what occurs there, that we need an overlap between the different computational domains, and what will be the local boundary condition, so h of end of the first process should be the first computed value of my second process, which is the value 2 of the IP, the process plus 1. And the same, what's the boundary condition of the first value of my process, of my right process, like IP plus 1, it should be the last computed value of my left process, IP. And this is like the important things for making this stencil code to run on MPI. One needs, this boundary condition to be properly set. Otherwise, one gets physical information that doesn't cross the domain. So those were the steps here on the README, where basically, we see that like to highlight the important steps of a distributed memory parallel code. And these steps would be that, well, one has to properly build our initial condition. This could be like here, setting our Gaussian to have a Gaussian spread and not 4 Gaussian if we run on 4 processes. This would be a bit more tricky, like if one has to read input data, one has to also distribute it properly. Then one has to initialize the global grid, like making these differences between the global and local domains. Then the second important thing is one need to make a boundary update in between each of the calculation. And finally, well, one needs to either reconstruct the global picture for visualization and finalize the distributed memory parallelization. And so basically, those are the kind of minimal 3 important steps for distributed memory parallelization. And those steps, they are handled by implicit global grid. So here, like it's kind of recalling this. And now maybe I want to, before we move to the code that uses implicit global grid, I want to show you a kind of simple 1D example that uses MPI. So just that you have that you can have an idea what's going on there. So doing our keeping our diffusion code, linear diffusion code that I was playing for with MPI, we can now write small code that does it. So I think here we have, so this is this 1D MPI.jl code, and this is like truly distributed parallel MPI code on the CPU in 70 lines. So what it does, first we have to call this MPI initialization, then we have to define our MPI kind of ecosystem or world. Well, we can assign the number of dimension to 0, so we can pass it on runtime. We have communicator, then we define the number of processes, or we get the variable for number of processes as function of what we of how many dimension we will define while running the code. Then we live in a Cartesian world, so we create our Cartesian world. We get me, which is a unique ID for every process, coordinates to know where we are in the global domain, and retrieve our neighbors. So basically each MPI process will know his unique ID, where he's in regards to the global domain and what his neighbors are. Then the physics is global, so there's no change there. NX is my local domain resolution. Then I can define a global domain resolution, or number of grid points, sorry, which is, I have an overlap of 2 here, so it's the number of dimension I have times NX minus 2 for the overlap plus 2 for the boundary points. Based on that, I can define my derived numerics, which should be the total physical length divided by the total number of grid points. I have my initial condition here that's defined with a x0, that's a shift to take account as function of my x coordinates. I have to shift by an x every process to have the correct Gaussian. And then there is my time loop, and in my time loop, well, I compute my fluxes, my update of height, and then there is one function here that's called update halo, and this update halo basically will do the maybe technically most challenging part, which is exchanging the local boundaries. And if we look at this update halo part, well, what we need to give is the array we want to exchange, which neighbors we want to exchange it with, and like the MPI communicator. So this would be, we exchange boundaries, local boundaries of our array H. Each process knows its two neighbors, and we have the MPI communicator. And what this update halo does, well, it will first check if I have a left neighbor, and if I don't have a left neighbor, this means that this value would be 0, then it will do nothing or exit. If I do have a left neighbor, then what it will do, it will copy the second value to a buffer and prepare a buffer to receive the first value, because that's what we want to swap on every local domain. We want to get the local boundary condition, which is the first value, and send the second value, which is the first physically computed value we have on the left of our process. Then we call the MPI send receiving function. That's what MPI is for. So I want to send what's in my send buffer to my left neighbor. So it's neighbor 0, and I want to receive my receive buffer from my left neighbor from the correct process. Sorry. And then what I can then do is, well, on what I received from my left neighbor, was written to the receive buffer. I can then assign it to the first value. This was for all this update halo is about, is I want to be able to receive the local boundary condition for my first value of A, and this was for the left neighbor, and for the right neighbor is the same. And here the entire exercise is I want to receive my local boundary condition for my last point of A. Well, and that's it. And then I can call this update halo function within my iteration loop, and each iteration I will exchange my local boundary condition, and then I can run that code and either visualize the results. Here I decide to save it to disk. And so each local domain, each MPI process will save its array, like the results, to disk, having me in the file name. And then I can use a visualization script that's here, that's also provided, where I can load the data. So let's see. It's here, so I can think I have the run function here, so I can use MPI run. I can run it on 4 processes, and then once it's finished, I can launch the visualization script in my other Julia terminal, and then it will should visualize. So what it prints that, well, I use 4 processes, that my X dimension or dems of 1 are 4, time it took, and the performance. And then if I go back to my Julia REPL, and I can then call the visme, I think 1D, and then what's not working? Nice thing. Where is this? What's not? Do say control. It's still under. I don't know why it didn't. To save control. But I will see what's. I will see what's not going here. But yeah, anyway, done. Yeah, now it's saved. And this fits in here. Interesting. Not sure. I will. I don't know. So just sorry for that little technical issue, but so now it should be in the correct. So now it should be launched in the correct repository folder. Yeah, now it's here, and then so let's visualize it. So here we go. So I had a Gaussian that was up to 1, and now it's kind of decayed. Yeah, so this is just to show, like, I mean, it's a nice working example that shows how one can use MPI and how we will, or how we are using MPI in implicit global grid. And this 1D example, and then, like, if you're interested, the 2D example that does the same, it's just, well, 2D, so a bit more complex. But yeah, that's the thing. Well, so far so good. So these are yeah. It's also maybe just not for simplicity. We're using here blocking communication because like it's just easier to implement for proof of concept. Yeah, so that's cool. We made this Julia parallel MPI code in 70 lines. That's pretty good. But yeah, now the idea is that we use this kind of what we just saw here. This is basically what's under the hood of implicit global grid. So implicit global grid basically takes this 1D MPI example that runs in distributed memory. On top of that, the main features that adds is that we use non-blocking communication, that we use basically one MPI process now doesn't only do, is not restricted to do calculation on a specific CPU core, but what we do is that we use MPI to launch or to handle a GPU. So with 4 MPI processes, basically we handle 4 GPUs. And also we implemented some advanced thing to prevent that MPI communication become a performance killer, because, well, as you saw in the workflow, we kind of in the code at every, if I take whatever code, but even the fake one, I do my local physics, but then every iteration I need to update my boundaries. And this update boundary, like this with MPI, sends messages over the network of your cluster of the supercomputers, and this can become like a performance killer. Yeah, if one has like thousands of MPI processes and 1,000 messages need to be sent, and you have a network with other user, well, you can get congestion and so on and so forth. So that would be like some things to handle there. So the last thing I will discuss here, and then we can go for the final wrapping up and the final Q&A, would be like to show one of these multi-XPU code where we basically combine parallel stencil to features from implicit global grid. And so yeah, I will start from the good performing XPU2 code that was written parallel stencil, and then add well, only 10 lines to make multi-XPU code. So those are the lines from the XPU code from part 2 that we'll have to change in order to make it a fully working distributed memory parallelization that can run on thousands of GPUs. So I will go back to my code and take this one and yeah, so here we are. Make 2 windows, and here we go. Yeah. So here on the left is the performing XPU2 code that kind of has 780 gig or 770 or 780 gigs per second memory bandwidth, and here's my multi-XPU code. So we see that now the main changes is to use the implicit global grid package and import MPI. Besides this, I have also to now define a global norm function that, well, implements now a global reduction on all my distributed processes. Then the important part, and this is really like one of the key and the driver of our implementation, is that the physics, the kernels, they're unchanged. So those, in the case of the XPU code, like that run on a single GPU, the global domain was the same as the local domain, and this was handled, and the physics were solved here. And on the multi-XPU code, well, now those kernels, they would just simply apply to the local domains and no longer to the global domains. But still on the local domains, you still solve the same physics. And this is usually like the core part of the domain science, like you don't want to start to messing around with your working physics. So the only changes are really like in how you wrap kind of this distributed parallelization around. And this with implicit global grid is really straightforward. So what you need to add is now, well, you need to initialize this global grid, and you give like the local grid points as input, and then you get out the global index and your dimensions. If we use GPU, there is a way to select GPU. This is relevant if you have multiple GPUs on the same compute node, and then it's like kind of, it selects the GPUs in an efficient way, and to assign the correct GPU to the correct MPI process. Then here, as in our proof of concept, well, now I have to use global grid points divided by total domain length to get my grid size. Do the same in the damping. And then no big changes. Some handling on the visualization, but this I won't touch here. It's kind of just to be able to reconstruct the global picture. And then, well, in the iteration loop, there is basically this update halo function where I make this boundary update, and this is the core of the MPI parallelization, and this is also the core of what implicit global grid exposes. So basically now I exchange H, and then I have to exchange my boundary of H within my computations. And then, well, the visualization here again, some changes where I can do in situ visualization and gather. So on the process that has ID 0, I will handle the visualization. And here, this is like, if I want this in situ visualization, I can ask to gather all local domains into a global domain or global array HV for visualization, and then plot it only on process 0. And then at the end, I finalize my global grid to clean up the parallel implementation. And so basically, I can run now this code, launch it with MPI, and this is what's shown here. So this code, I can, if I put the do visualization flag true, it will generate automatically generate a GIF. And here I run it like on 4 V100 GPUs, like on this 496 by 496 global resolution. So it was 248 times 248, each of the 4 local domains. And yeah, it solves my diffusion equation here that does the nonlinear diffusion. So that's cool. We have this GPU MPI parallel diffusion nonlinear diffusion solver that runs like great. Maybe I can now put this here and show you some of the one advanced feature. So one thing I didn't discuss is that parallel stencil in combination with implicit global grid provides this hide communication macro. And basically, this hide communication, what it does is it overlaps MPI communication with physics calculation. So the idea is we look for a simple way to not to lose performance if you have to send MPI messages around. So if you recall here, it's the one challenge is that the boundary update of our working array H is in the most inner loop of the algorithm. So every iteration will update H, and then we have to update the internal or local domain boundaries with the MPI communication. And this can be costly because, well, during this boundary exchange, the calculations are on hold. And then, like, if you have a slow network, if you have many users on the cluster, on the supercomputer that puts pressure on the network, well, communicating every iteration can become costly. And then, well, the bigger or the more MPI processors are involved in the calculation, the more tricky it can get to keep up with the performance. So, well, if one would do a weak scaling, performance may drop by including more and more MPI processes, just because, like, well, there's more and more time and congestion that occurs with them with sending MPI messages. So one easy or one one easy thing to circumvent this is to try to say, what if I first compute a couple of like my boundary points, and then I start to do the MPI update on those boundary points, and in the meanwhile, while these boundary points are getting updated with MPI, I compute the inner points of my domain. And this is what's done with this height communication. So in this height communication, I say that in the X direction, I first compute 8 grid points at the boundaries in the X direction and 4 grid points at the boundary on the Y dimension. So I call this compute update function on those outer or boundary points. And then once this is done, I start to exchange those boundaries with MPI. And during this exchange, I basically recall this compute update function to compute my inner point. And like this, you can, it needs some investigation, but if you have the right ratio, you can actually fully hide the MPI communication behind computation that you would anyway do. And so you can totally hide the basically MPI sending things. Yeah, so one kind of, this goes already towards, so this is the last thing I would speak about, and then we can end with a Q&A. So this is what's kind of showed in the advanced features of the README, that this height communication capabilities is like combining parent stencil and implicit global grid. And the way to check that everything is working correctly, one can do some profiling, and that goes along the line as what Tim and Julian and Valentin showed on the first workshop. So here one could use nSight or the NVIDIA Visual Profiler. Here I still use the NVIDIA Visual Profiler, but the concept is the same. So one launches the Julia code with MPI, but now calling this NVProf profiling. And then in the code, one has to add, so the code is also in the extras. So let's look at this. So for the profiling, basically what one has to add, this CUDA, the profile statement around what I want to profile. So here I profile basically my physics in the while loop. And so if I execute this, code using this command, it would generate one profiler file, automatically generated file per MPI process, and then I can load that file in the NVIDIA Visual Profiler. And this I already did here. And this is how it looks like. So yeah, I think it's this one. So what one sees in the launching the NVIDIA Profiler is that there is the compute somehow stack trace. And so the green, let me further zoom in. So if I now look at a specific place, the green thing here is my compute update kernel. And so what happens is that this compute update kernel is called 4 times, because I have, in 2D, I have 4 boundaries. And so this is like the summed up the summed up trace. And this is like on what's called different streams on the GPU. So basically my compute kernel is called once per boundary to compute the given number of boundary points I specified in the height communication. And then once this is done, it's called, here it's the long chunk, because, well, they're much like, imagine, 1048 times 1048. There are only a couple of boundary points, but there's a lot of work to compute the inner part. And so as soon as I'm done with computing my boundary point, I start the MPI sending. These are these purple dots. And so there is some, well, it's purple dots. There is some latency with MPI. There is some maybe congestion in the network that may spread those MPI communications like over time. But important is that here, while this MPI communication occurs, I do work that I have anyway to do, which is compute my inner points, compute my physics. And so like this, I could save a couple of microseconds in that example. Otherwise, if I wouldn't have this hide communication feature enabled, basically I would stop here with the previous kernel calculation. I would have wait a couple of microseconds to have the MPI communication done, and then I would start with computing the next step. And now here, one sees that this nicely overlaps. And this is here in 2D at quite high resolution, but it gets a bit more tricky. So when you get to 3D, when there is more work to be done, more field to be exchanged with MPI, well, I mean, for now, we always manage, but then it's really important because basically time it takes for MPI communication is more or less, can be equal to time it takes to compute the physics kernel that computes the rate that you want to send with MPI. So there, like in 3D, for example, for 3D stocks or 3D solvers, it's crucial to have this hide communication feature because it's really like, you can nearly just overlap it with the physics calculation, and like then you benefit really, really a lot. So yeah, I think that's it. Well, since all the examples are in the repository, you can really play also with this MPI code to see like the effect of having this hiding communication enable or disable. You can just comment it in the code and rerun it. And if you try to make a scaling over many GPUs, you will see that performance in one case will not keep on par with as if you do the weak scaling. While if you have the hide communication feature, well, you will keep up with performance. And maybe the last remark is about CUDA or MPI. So implicit global grid supports CUDA or MPI. So if you have a compute node, a cluster, a supercomputer where the local MPI install was done being CUDA aware, so that MPI can directly exchange GPU arrays, then you can set the implicit global grid CUDA aware MPI flag to 1, and then implicit global grid would basically use the CUDA aware features without you have to change anything in your code. So that's the kind of the little sugar at the end. Well, yeah, so that's it for the third part about distributed GPU computing. And then, I mean, with those codes, now if you have a supercomputer that has like thousands of GPU, you can just run that code on thousands of GPUs. If you have so everything we presented today and all the this particular 2D nonlinear diffusion example, so all the material is not limited to that example. So basically, I think especially the MPI GPU implementation can be really interesting for 3D calculation, large-scale 3D calculation. And so I would really recommend that you check out the mini-app section from the parallel stencil README. And there basically, well, first there is some extended discussion about the performance metric, but then maybe what's of interest for many domain scientists is that we made a collection of different physical problems, like different problems for various domains of science that are solved using implicit global grid and parallel stencil. So there are some 2D and 3D applications. And for example, this was also one question of the pigeonhole. So if I go to the acoustic 3D, so this is like a acoustic wave propagation in 3D. This is just a 2D slice. And well, there is like a 3D and a 3D multi-XPU example. And for example, this animation here is like one slice of this 1000 cube that will solve on 8 GPUs. And basically the code is also there. So it's the same code basically as the nonlinear diffusion equation in 2D. Now it's just a wave propagation in 3D, but it has the hide communication feature. It can run on CUDA or MPI, and it uses this very mat close implementation that's permitted with parallel stencils. So yeah, this is like a 86 lines of code, acoustic wave propagation in 3D that runs on MPI, GPU, CUDA, with high overlap of communication and computation, for example. So yeah, I would really suggest that if you have interest, you go there and like check out the codes and try to tune them for your needs. Well, yeah, I think on my side I'm pretty much done. So yeah, I don't know if Mauro and Sam have some Q&A. We should look at. Yeah.
Hi, Ludovic. Well, thanks a lot for your stuff on the MPI and implicit global grid. There is not that many questions anymore. I think maybe a few people are tired by now. I thought one interesting question, which maybe we could briefly discuss, is if we do parameter estimation, does the package provide the function for calculating sensitivities? And I thought that might tie in a little bit with your inversion work you've done before.
Yeah, that's a good point indeed. So the package, or the packages, so in parallel stencil and implicit global grid right now, they don't provide, maybe yet, can add any helper function to do parameter estimation or sensitivity calculations. This is like there are two paths there. So one is well, in a do-it-yourself fashion. So one can, like, there's work that should be out soon and will be also appearing in the parallel stencil mini apps, I think, like to write, like, for example, inversions using adjoint, like retrieving gradient via the adjoint approach. And then when you use the adjoint, you can have the sensitivity kernel that come up more or less for free. But this can be like very handwritten or manually implemented. And this is work we've done. There's the last year JuliaCon, or at least my last year JuliaCon presentations is about that. I can add the link on the written reply. And yeah, the second part of the answer is that's this ongoing work, I think, with diffec, that, well, there would be interesting to see if the parallel stencil plus implicit global grid high performance GPU computing framework could be used to kind of have synergies with diffec, like .jl, where one could then basically use packages of that ecosystem for automatic differentiation to retrieve like gradient or make sensitivity analysis. But like with this high performance backend that would, or partly backend that would then provide parallel stencil and implicit global grid. So yeah, we'll see a bit how that evolves, but that would be like the direction for this to go.
Just to add one more thing there. So let's say if there's a good way to do these calculations in a stencil-based way, right? Then this could go in some little submodule, like finite differences 1D, 2D, 3D are there. So this could go into another submodule which could be loaded in addition, and to provide such additional functionality.
Yeah, I think that's as far as I see all the questions from the Pigeon chat. So I think maybe we can wrap it up here. So I'd like to thank all of you for listening. I'd like to thank Ludovic again for putting this I think, really great course together. And yeah, having the initiative to run this workshop. I'd like to thank Sam for putting all the code together and making everything work. So yeah, well, thanks a lot to everyone.
Yeah, cool. Thanks, Mauro, also for your support and participation. And yeah, again, well, I really hoped you enjoyed that workshop. And yeah, feel maybe if you try out Parallel Stencil or Implicit Global Grid, or you have any questions, feel free to ping us on Discord. And yeah, and I mean, maybe not. We're happy to help or assist or see if there's something that could be done. And yeah, have fun using those packages and have a nice evening.
Okay.
Yeah, thanks also from my side, everybody. And just let us know if you have any comment, like suggestion of what you think would be great to have in these packages, what you particularly are missing, right? All right.
Cool. Okay. Goodbye. Thanks, everyone.
Bye.